Hello students. Topic 6 is on exact ODEs. We're going to do a few slides of review first. Given the curve capital F of x comma y is equal to c in the xy plane, the slope of the tangent line at any point xy can be found through implicit differentiation as demonstrated below. Now this was a topic that should have been covered in a Calc 1 course. So we're going to find the slope of the tangent line at all points on the curve below corresponding to x equals 1. I've given the equation of the curve and also the graph of the curve. A couple things to notice. That this curve does not pass the vertical line test. Therefore, it is not a function of x. Nor does it pass the horizontal line test. So this curve is also not a function of y. Whenever you're given a curve where it's defined by just any old expression you want involving x's and y's equals a constant, then all bets are off as to whether this will wind up producing a graph that is a function of x or a function of y. But we can still do calculus and determine slopes of tangent lines at various points. Now, implicit differentiation looks like the following. You take your equation exactly as it's written. You can even move pieces around if you'd like. For example, if you want to solve for y first, you can, if that's possible, or solve for x first, if that's possible. Or you can just differentiate it exactly as you see it. And you do a derivative of both sides with respect to x. Now we're going to assume, this is implicit differentiation, so we're going to assume that there is a dependent relationship between x and y. That if you tell me what x is, then this equation will dictate what y has to be. So let's assume that each y you see is a implied expression that is dependent on x, and we'll treat the x as the independent variable, as indicated by this dx. So when you see the product right here, x times y squared, we have to use the product rule, because we have x, which is a function of x, times y squared, which is an implied function of x, or implied, it's dependent on x. When I do this, we get the derivative of the first, derivative of x is 1, times the second, plus the first, which is x, times the derivative of the second. Now to differentiate an unknown expression squared, where that expression depends on x, we must use the chain rule. So the derivative of y squared will be the power rule, 2y to the first, but then times the derivative of the base, times y prime. Now this y prime is really a dy dx, but I'm going to be lazy and just write down y prime. Minus. Now we have to use the product rule here as well. So I'm going to put some parentheses because of that minus, and apply the product rule. The derivative of 2x squared is 4x, times the second, so times y, plus the first, which is 2x squared, times the derivative of y, which is simply y prime. And then is equal, and then we differentiate the 3, which we get 0. Now what we want to do, let me move that down slightly, is solve this expression for y prime. So I'm going to distribute the negative across the parentheses first. Let me just copy this and paste. Distribute the negative across the parentheses, so that becomes subtraction. That will be subtraction as well. Group the terms that have y prime on the same side. So I'm going to copy this again. So if it doesn't have a y prime attached to it, we're going to move it to the other side by adding, subtracting as appropriate. Just keep the y prime terms together on this side. Push that over there. Let's move our equal sign over here. And then we have to do opposite signs, of course, to get these onto this side of the equation. So we have negative 1y squared, positive 4y. Positive 4xy. And I don't really need that 1 times. Let me get rid of that. So we just have negative y squared. When you're at this stage here, now you factor out the y prime on the left side and then divide. So I'm going to do both those steps at the same time. First thing we do is factor out this y prime. it would leave this expression after y prime is factored out, but then we're going to divide all of this down to the other side. Okay, so we're going to have a division bar right there. This will be gone. And let's clean this up. There we go. So y prime will be negative y squared plus 4xy all over, and then I'm just going to rewrite this as 2xy minus 2x squared. So here's an expression that will allow us to find the slopes of the tangent line if you tell me the point at which you're focused on. So here are instructions were to find the slope of the tangent line at all points on the curve corresponding to x equals 1. So x equals 1 is right here. There are 2 points on this curve where x is 1. How do we find them? Well, graphically, it looks like 1, 3 is a point, and it looks like 1, negative 1 is a point. Let's see if we can confirm that those are, in fact, the 2 correct points. The way to do that, let me move this out of the way so I can see that better. Okay. The way to do this is to rewrite the original equation. So you have xy squared minus 2x squared y is equal to 3. And replace x with 1 and solve for y. So we're going to evaluate this at x equals 1. That produces, we have y squared minus 2y, and then I'm going to subtract the 3 over to get a 0, so I have a quadratic in terms of y, and I can factor that, y minus 3 and y plus 1, and then solve this for y, and you see you get the 3 and the negative 1. Let's put this here. So y is equal to negative 1 and 3 are the 2 different y coordinates when x is 1. So that confirms what appeared to be the case in our visual. 1, 3 is a point on this curve, and so is 1, negative 1. So we have to find 2 different slopes of tangent lines, and they may not be the same result. To find out the slopes of the tangent lines, you simply plug in into your y prime expression the point 1, 3 in for x and y. Let's do that work down here. So I'm going to say, what's y prime evaluated at the point 1, 3? Okay, I'll do most of this work in my head right here as we're plugging into. So we have negative 9 at the top, plus 4xy, where x is 1, y is 3, so that's plus 12, all over 2xy, 2 times x times y, where x is 1, y is 3, will be 6, minus 2x squared, this is going to be minus 2. So we wind up getting 3 in the numerator and 4 in the denominator, so 3/4. So at this point right here, we expect a slope of 3/4, which would mean we would need a rise of, I'm just going to draw any line that has a slope of 3/4. So a rise of 3 or run of 4. So if I started at the origin, I'd want it to go through that point right there. This would have a slope of 3/4. So I'm going to just make that line. There we go. And then I should be able to just park that right there on the curve and say, yep, there's our tangent line. Going right through our point. The slope of that line is 3/4. Now, how about at the other point? So y prime at the point 1, negative 1 is equal to, all right, so I'm looking at this again right up there and plugging in 1 for x and negative 1 for y. So we get a negative 1 up top, 1 for x, negative 1 for y, so minus 4 all over 1 for x, negative 1 for y, negative 2, and then minus a 2. So this gives us negative 5 over negative 4, or just 5/4. So a slightly different slope. To make a 5/4 line, I'd want to make a line that goes rise of 5, run of 4. So it'd have to go through right up there where that m is, essentially. So I'm going to draw a line first that has the correct slope. I can just draw any line, really, with this particular software. I wanted to get rid of that dot. I didn't mean to put that there. Okay, let's park this line right there and then make the other vertex be right around there. So that's a line whose slope is 5/4, and that should be the tangent line slope right going through that point right there. Bingo. So we have a slope of 5/4. Okay, and this is implicit differentiation. Let's go on to the next slide, which is also review. This is review of material from a Calc 3 class. And I realize that some of you maybe haven't had a Calc 3 class, but this is a very simple idea that we're about to do. It's called a partial derivative. Given a function of two variables, capital F of x comma y, its two partial derivatives are defined as follows. So let's do this first one here. This is not a d, it's called a del. It's a Greek letter. It's a del x. This means you're doing a partial derivative of a function of two variables. And another notation for this is putting capital F with a subscript of x. That means do a partial derivative with respect to x. And the way you do that is you differentiate the function f like you would normally. You treat x as the independent variable and y as a constant. So every y you see in the expression, you treat it just like you would any constant, and the x is what you think of as the independent variable. Now when you do this, and then you plug in a point AB, what this partial derivative tells you after you plug AB into the partial derivative, it gives you the rate of change of f at the point AB in the direction of x. That conceptual idea isn't super important for this class, but I just wanted to remind you of what a partial derivative means. The other partial derivative that you can do is a derivative with respect to y. So you do a del y, which means doing a partial derivative, which means every other letter you are assuming as a constant, and only the y's you treat as the independent variable, as this states here. Another notation is doing capital F subscript y. That means we've done a partial derivative with respect to y. And when you do a partial derivative with respect to y and then plug in a point AB, this gives the rate of change in f at that point, but in the direction of y. So in other words, you can think of it as slopes in different directions, because the graph of a function of two variables creates a surface. And when you're standing on a hill, on a surface, if you will, and you look in the direction of x, the hill might have one steepness, but when you look in the direction of y, the hill might have a different steepness. So this is what is sort of meant when we're talking about the rate of change in different directions. Three-dimensional thinking is coming into play here when you're imagining that. Okay, suppose the temperature in degrees Celsius of a plate at the point xy in inches is given as follows. Find the rate of change of the temperature at the point 21 in the directions of x and y. All right, so we just have some sort of plate, and there's different points on the plate, and this function here tells us the temperature at a point. So we have this varying temperature across this plate. And we're going to say how the temperature is changing at the point 21 in various directions. Like maybe if you're sitting on the plate at the point 21 and you head off in the x direction, maybe the temperatures will drop if you go that direction. But maybe if you go in the y direction, the temperatures will rise. So the partial derivatives are how we determine those rates of change in the two different directions. Okay, now doing these derivatives is fairly straightforward. It's not like implicit differentiation. Like when I did implicit differentiation on this, I treated x like the independent variable, and I treated y like a dependent variable on x. Whereas when I'm doing a partial differentiation now, I'm going to treat the y like it's just a constant. It's going to totally change the result I get here. So t sub x, this is our partial derivative with respect to x. So normally if I said, hey, what's the derivative of 6x to the fifth, you would just leave the 6 and then do the power rule on the x. Agreed? And you would say 30x to the fourth. Well, in this expression here, this y cubed we're treating like a constant, not like a function. So I don't need to do the power rule. Or sorry, the product rule. This is just like having a constant in front of x to the fifth. So when I differentiate this, we're going to have x to the fifth will be differentiated and get 5x to the fourth, and the constant will just stay. And that's it. Now, if you did do the product rule on this, just review what that would look like real fast. You would say, okay, what's the derivative of the first? That's 5x to the fourth times the second. And then you would say plus the first, x to the fifth, times the derivative of the second. Well, the second, we're treating y like a constant. So you might say the 3y squared, but then as soon as you do the derivative of the base, We're thinking of y as a constant, not as a function. If you think of it as a function, you would say y prime. If you think of it as a constant, then you do the derivative of a constant, which is 0, which kills this whole term, giving you the same thing you get right here. So it's a very different mindset when you're differentiating partial derivatives than when you're doing implicit derivatives. Let's continue. The derivative of x is 1, and the derivative of natural log of y. Well, since y is a constant, the natural log of y is just a constant as well, so that just differentiates to 0. Now we're going to do the next partial derivative with respect to y. Here we treat all the x's like constant and differentiate the y's. So this x to the 5th is a constant. That's just going to stay in front of this y cubed, but then I differentiate the y cubed, and I get 3y squared. So ultimately we have 3 x to the 5th stays, y squared. Plus, the derivative of x will be 0, because we're thinking of x as a constant. It goes away. But the derivative of natural log of y is negative 1 over y, when I think of y as the independent variable. So these are the two partial derivatives. Now I just have to plug in the 0.21 to get my results. So plug in 2 for x, 1 for y. And we're going to get, let's see, 2 to the 4th is 2 times 2 times 2 times 2 is 16, times 5 is 80, times 1 cubed, that stays 80, then add 1, we get 81. Now this is a rate of change. This means that we are in the direction of x. So here's the 0.21, and when you try to go this direction on the plate, the temperature is going to be, its derivative is positive, 81. The temperature is increasing at 81 degrees Fahrenheit per unit change in x, and this was measured in inches, so per inch. So this is the rate of change of the plate in the direction of x. 81 degrees Celsius per inch is how it's changing in temperature. At that moment, at that point in the plate. Now, as soon as you get to the next point, the rate might increase or decrease, like an accelerating car or something. But at that point, in that direction, the temperature is increasing at 81 degrees Celsius per inch. Now let's do the other direction. So now we're at the same point, 2, 1, but we're thinking in the direction of y, how is the temperature changing? That's what ty will tell us. So plug 2 and 1 in for x and y into ty, and 2 cubed, let's do that part first, is 32, times 3 is 96, times 1 squared. So just 96, and then minus 1 over 1, so minus 1, so 95, if I did that correctly, hopefully I did. So in the direction of y, where temperature is increasing at 95 degrees Celsius per inch. And we get the rate of change in the direction of y. Oops, just get rid of that image there. And we'll summarize here. Okay, now we're going to get to our differential equations material. Suppose capital F is a function of two variables, x and y. It has defined partial derivatives in some rectangular subset of the xy plane. A first-order ODE is exact in that same rectangle if the ODE can be written in the form below. So here's our differential equation. We have some expression right here that turns out to be a partial derivative with respect to x of capital F. And then we have some expression here, which happens to be the partial derivative of capital F, but with respect to y. And then times our y prime, and this is your classic y prime, dy dx, is equal to 0. So if our ODE can be written this way, where this part and this part are the x and y partial derivatives, respectively, of some other capital F function, then we have an exact ordinary differential equation. And it turns out that the solution, the general solution to this exact ordinary differential equation, is implicitly given by this expression. So the capital F function set equal to c, where c is the arbitrary constant that makes this a general solution, and this will give us our solutions to the differential equation. So it's actually very easy to create an exact differential equation. You simply have to write down pretty much any capital F function you want, do its partial derivatives, and then write this. And you've created a differential equation that's exact. We're going to do that for the temperature function that we were just analyzing. Okay, so let's get these partial derivatives again. So tx, the partial derivative of t with respect to x, I'll leave off the xy. Derivative with respect to x, treat the y's like constants. So we get 5x to the 4th times y cubed plus 1. And the natural log of y will go to 0 because y is a constant. The derivative of t but with respect to y. So we'll back up to here and do the same thing, but this time treat x like constant and y like the independent variable. And we get 3x to the 5th y squared plus 0 and then minus 1 over y. So if I take this tx and I write it first, so 5x to the 4th y cubed plus 1. I'll go ahead and put it in parentheses, although you don't need to. And I add to this the ty, which is, and this one should be in parentheses because it's going to be multiplied by y prime, times y prime, and set this equal to 0. And just like that, we've created a differential equation that's considered to be an exact differential equation. Now what we want to do is verify that we have a general solution. So I might move some of these pieces around. I'll move this right there, I'll move this right there, and then I'll put the differential equation we just created right below it. Okay, so this gives me room now to rewrite the original t function, which is x to the 5th y cubed plus x minus natural log of y, and set this equal to c. So here I'm creating a general solution. Whatever this curve, whatever this looks like when you graph it, it might be a function of x, might not. It might be a function of y, it might not. And you're going to get different graphs as you change c to different variables. But we're just going to see, we're going to use implicit differentiation to see if, in fact, we are working with something that's a solution to this differential equation over here. Okay, so let me move this c over slightly. Let's introduce the implicit differentiation. We're going to differentiate regular derivative with respect to x, meaning this time when I do my implicit differentiation, I'm treating the y's like implied functions of x. That's different than partial derivative. So differentiate, we have to use the product rule in the first part. Derivative of x to the 5th is 5x to the 4th times the 2nd plus the 1st times the derivative of the 2nd, which is 3y squared times y prime. All right, we can't say y prime is 0. We can't zero this all out because we don't know what y is. It's a dependent expression on x. Plus, now I don't need the product rule for the derivative of x with respect to 1 is just 1. And then when I do the derivative of natural log of y, we get y prime over y. Remember, the derivative of natural log of an argument is argument prime over argument. That's the chain rule happening. And then the other side, it doesn't matter what the c is, the derivative will be 0. And now I'm going to solve for y prime. And I see two terms that have y prime and two terms that don't. I'll leave the two terms that have y prime on the same side of the equation, which is namely this term and that term, and factor out the y prime at the same time. So that leaves us, we have x to the 5th. Let me put the 3 first. We have 3x to the 5th y squared, and the fact y prime will be factored out, minus 1 over y, and the y prime is factored out. The other two terms, the 1 and this first term, I'm going to subtract to the other side. So we have minus 5x to the 4th y cubed, minus 1, and here we go. Now I'm going to solve for y prime. So I do a lot of copy pasting here. Copy, paste. It'll be that expression divided by, and then let's just copy this right here. Copy, paste. Now it might be off-putting to have this fraction be within this overall fraction, and so a quick strategy to get rid of that issue is I'm going to multiply my answer by y over y. And this will give me a version that doesn't have that's not a complex fraction. So we get negative 5x to the 4th y to the 4th minus y all over 3x to the 5th y cubed minus 1. Okay, so now we just want to verify that this, in fact, is a solution. By this, I mean this y when I plug this in for y prime right here, that in fact this differential equation will be satisfied. So here we go. Let's copy and paste. Copy this, paste. Let me shrink it down just slightly. And I'm going to replace the y prime with this expression. Actually, I'm now seeing the advantage of not doing what I did. I'm going to go ahead and leave it a complex fraction and not do this. Just use this. Right here goes in for y prime. Now can you see why I chose to do that? So right now we're checking to see if we get 0 out of this. Because this expression right here is exactly what I see down here. So they cancel each other, leaving just this part right there. Okay, so that cancels with that. And we are left with 5x to the 4th y cubed plus 1. And then the numerator, which is minus 5x to the 4th y cubed minus 1. And sure enough, we get 0 is equal to 0, check. All right, so to create and solve an exact differential equation is extremely easy because you simply start with any function of two variables you want. You do partial derivatives for x and y, and then you create a differential equation. And then it turns out that this exact same function, when you set it equal to c, and think of it as representing a curve on the xy plane, forms the general solution to the very differential equation you just created, which we just confirmed by setting the t function equal to c, doing implicit differentiation, not partial, getting y prime, plugging y prime in right here, and then showing that this whole side zeroes out. Okay, let's keep moving on. Now the challenge, of course, is going to be what if you're given this as the starting point? Then you sort of have to determine whether this is exact in the first place. In other words, is there a capital function where this part here is the partial derivative with respect to x, and this part here is the partial derivative with respect to y? If the answer to that question is yes, and we can find it, then all we have to do is set this equal to c, and we've created a general solution. So starting with the answer, easy to create the differential equation and the solution. Starting with the differential equation, the challenge will be how do I go backwards to this part? All right, suppose an ODE has the form below, where m and n are continuous in some rectangle. So now I'm just saying some expression and some expression, times y prime is equal to 0. Then the ODE is exact if you do a partial of this part with respect to y, and then a partial of this part with respect to x, and you wind up getting the same result for all points in that rectangle. Let's assume that this was exact to begin with. That means that there was some f where m was the same thing as fx, and y was the same or n was the same as f sub y, the partials with respect to x and y. So that means if I start with m, which is really f sub x, and I do m sub y, then I've done another partial derivative. I've started with fx, and I do now another derivative with respect to y. So I'm really doing a second partial derivative, once with respect to x, followed by with respect to y. And then if I do the same thing, if I start with n, which is f sub y, and I do a partial with respect to x, then I've done f sub yx. And then there's some theory in Calc 3 that suggests if f is a continuous function, then its partial derivatives in either order will yield the same result. So this, if I can show that the second partial derivatives are the same, that implies that these were in fact partial derivatives of some parent function f that we started with. Okay. That's all I want to say about the theory of that. Let's just move on with how to apply this. Okay, determine whether each ODE below is linear, separable, and or exact. We're going to do the linear and separable first, because we're familiar with those. And then I'm going to use what was just stated right here to determine if these are also exact. All right, so linear. I see to be linear, the dependent variable and all of its derivatives have to be raised to the first. So you can have a term with any x's or constants you want times a y prime, then somewhere a term with any x's or constants you want times a y, and then if this was second degree, then a term with any x's and constants times a y double prime, etc., depending on what degree or what order our differential equation is. Notice that all of these are, the highest derivative I see are all first order. There's no second orders thrown in here. So I do see a product of y prime and I see a product of y's and y primes. This is a problem for being linear. The y squared all alone is a problem. Remember, to be linear and first order, you have to be able to write your differential equation in the following way. Some function of x times y plus some other function of x. Right? This was the most general form of a linear differential equation. Can I write this particular differential equation in that form? The answer is going to be, let me undo that. The answer is going to be no. Notice I have a y prime in a couple places. So if I move this over, I'm going to subtract that term over to the left side and move this term over to the right side. Factor out the y primes. We have e to the 2x plus 3y squared with a y prime factored out is equal to 2y e to the 2x. Divide both sides by this e to the 2x thing, and we are going to see a definite problem here. Right, there's no way that I can somehow tweak this side here so that I see just some sort of expression involving x times y only, plus maybe a second piece over here. Because I've got y's there and y's there, so I can't factor the y out. If I could factor, I mean, if this term y squared wasn't there, then I could grab this one, this y right there, and factor it out, and then call all of this here the a of x. And this one is linear. But I can't factor out a y and do that. So this is nonlinear. I'm going to just delete all that for space sake and just point at this term right here. Just indicate the issue. The fact that we have a y squared lying around here, this is definitely a nonlinear term. Okay, the other one does appear to be linear. I can solve for y prime, just have to do a little bit of division, and I'll put the y prime first. Divide by the negative 4 sine x, we get negative cosine x over sine x, that's cotangent of x times y. So definitely this is linear because there's my a of x and my f of x is just 0. So we have y prime equals a function of x times y plus some other function of x, which could be the 0 function. So this is linear. The last one looks pretty similar. Only one subtle change. There's a cosine 2x instead of a cosine x. So when I do the division, I won't be able to say cotangent, but I can still do this. Solving for y prime is going to wind up being negative cosine 2x over sine x times a y. This is still linear because here's my a of x function times a y plus a 0 f of x. So we have another case of linear. Okay, let's examine separable next. If after you've solved for y prime, so I'll have to go back over here and remember what y prime was when I solved for it. I think I can do this. This is 2y e to the 2x over, and it was e to the 2x plus 3y squared. Okay, so this was y prime. If it's possible to factor this into a function of x's, then times a function of y, so you have some sort of f of x times some sort of g of y. If you can factor that in such a way, then it's separable. But I can't see a way to factor this in a way that we have x's and y's as break this apart into a function of x times a function of y only. And so this, if that's the case, if you can't do it, then this is not separable. I'll just put not separable. The next one, notice that factoring is already done. Split it right there. Here's a function of x, here's a function of y. In fact, this linear function is also, what the word is, homogeneous, because the f of x function is 0, and all homogeneous linear equations are separable. And they separate easily by just divide by the y. I'm going to change the y prime to dy dx, and divide by the y, so we have 1 over y dy equals, and multiply the dx to the other side. So this is definitely separable. Got the y's and the dy's together, and the functions of x and the dx together. Well, this next one is also separable for the exact same reason, because it's also a homogeneous linear equation. The f of x part is 0, and all homogeneous linear equations are separable. Divide by the y. Oops. Let's go back to black. Here we go. Divide by the y times the dy equals, and then... Now, whether or not you can actually integrate both sides of this is a different story, but we can certainly separate them. Okay, so we have the first two of them are linear and two of them are separable. And let's see which ones are exact. Now, to determine whether it's exact, you must now try to put your differential equation in this form. To get a 0 on the right side and everything else on the left side, and factor out the y prime from all the y prime terms. So we got to do that first. So I'm going to add this expression over to the other side and factor out the y prime. So we have 2y e to the 2x plus, parentheses, e to the 2x plus 3y squared with a y prime factored out. Okay, so I have this general structure. This is the m, and this right here is the n. Let's indicate that. Now, to determine whether this is separable, I have to do a partial derivative of m with respect to y, and then do a partial derivative of n with respect to x. And if I get the same thing, then we have a separable differential equation. Okay, now I want to do a derivative of m, but with respect to y. So treat the x like constant, which means that the e to the 2x and the 2 are all just like a constants times a y. And when you differentiate a constant times y with respect to y, you just get the constant. So you just get the 2e to the 2x. Now we're going to differentiate n, but with respect to x. The derivative of the first part of n, e to the 2x, with respect to x, we use the chain rule, we get 2e to the 2x. And then the derivative of the next part of n, 3y squared, with respect to x. That means y is treated like a constant. So that's just one big constant right there being added, so its derivative will be 0. And because these are the same, this means our ODE is exact. Oops, get rid of that. Oops. How to say that? Okay, so ODE is exact. Let me move that down, just give myself space. Now let's try the next one. I'm going to zero out the right side of this equation by adding what I just circled over to the left. So that gives us 4y cosine x plus 4 sine x y prime. I'll put the y prime there at the end is equal to 0. Okay, so there's my general structure that mimics this structure right here. So identify the m. The m is our first part here that does not have y prime, and our n is the 4 sine x that does have, that's a coefficient of y prime. Now we just need to do m sub y and n sub x and see if they're the same. M sub y, the derivative of m with respect to y. So once again, there's just a single y right there, so it's cosine of x and the 4 are constants as far as this is concerned, so this is just like a constant times y. And the derivative of a constant times y with respect to y is just that constant. So you get the 4 cosine x. Now we do the derivative of n with respect to x. Well, n only has x involved in the first place, and the derivative of 4 sine x with respect to x is 4 cosine x. So once again, these are the same, which means that our ODE is exact. So you can see it's a rather easy test. As long as you don't mess up your partial derivatives, it's a rather easy test to determine whether your ODE is exact or not. Just got to do a little bit of tweaking of this so that you get it in the right form. So once again, I'm just going to add, we have 4y cosine 2x. I'm going to add the 4 sine x times y prime, put the y prime at the end, just so it matches, our form right here. Identify the m and the n. This time m is this 4y cosine x. And the n is the 4 sine x. And this time when I do my derivative of m with respect to y, I get 4 cosine 2x. But when I do n with respect to x, I get 4 cosine x. So not the same. So the ODE is not exact. All right, so there's a simple test for determining whether we have exact. Now let's talk about how to solve an exact equation once we find it. So this is the same differential equation that we just did in the first column here. So I'm going to do some copy pasting. Let's grab this. Okay, so first thing to do is put it in the correct form, the form being some function of xy plus some other function of xy times y prime is equal to 0. It's exactly what we have right here. Determine whether the ODE is exact, and we've already done that. Let's say see above, or see the previous slide. That's been done. Now we want to try to figure out, now keep in mind that this function here was some function, was the result, it was the result of doing a partial derivative of some function f. And this is the result of doing a partial derivative with respect to y of that same function f. So we just got to work backwards and try to figure out what f is. We got to do some reverse partial derivatives. So the next step, number 2, is to find, we're going to create a capital F function. I'm going to leave off the f of the x and y, and we're going to integrate the m function with respect to x. So put the m function, which is the 2y e to the 2x, integrate that with respect to x, and then add to this some function of y. This is like adding a constant after you do an antiderivative, because we're doing an antiderivative with respect to x, so any function of y would be like a constant with respect to x. Doing an antiderivative with respect to x of this expression, the 2y is treated like a constant, so we've got to anti-differentiate e to the 2x, which is itself divided by 2. So we get capital F is equal to the 2y stays as a constant, and we get a 1/2 e to the 2x, plus some constant with respect to x, so some function of y, g of y. Now, and it could be helpful to cancel that 1/2 and the 2 first, so let's do that. So f equals just y e to the 2x plus some function of y, g of y. Next step, step 3, find f sub y. So we are assuming that we found our capital F function, but there's still a piece of it we don't know. But it should be true that whatever this capital F function is, when you differentiate it with respect to y, it should be equal to the n function right there. So we're going to find the derivative of our capital F function next with respect to y. So this e to the 2x is like a constant as far as y is concerned. So we have e to the 2x times y, the constant times y, and the derivative will just be that constant. So it'll be just e to the 2x. And then we have to do the derivative of g with respect to y, so it'll just be g prime of y. Now we set this equal to the n function. Right, our n function, let's be clear about this on the same page, right? This was our m function here, and right there is our n function. So set this equal to the n function, which means I'm just going to copy paste. and replace the n there with the actual n function, which is e to the 2x plus 3y squared. So there's the n function. Next is solve for g prime. So get g prime isolated. Notice the e to the 2x's cancel each other. So to solve for g prime, we just get g prime is equal to 3y squared. Okay, so we've done steps 1 through 4 now. Step 5, determine what g of y is from g prime. So I've got a g prime equals 3y squared, and it could be any g function. So do an antiderivative of 3y squared, we get y cubed. You could put plus any constant there you want, but we just need one specific answer. Do any specific answer. Let's just get rid of that. So y cubed will be our g of y. And then we have a general solution, because we go back to what we said our f was, which was right here. We now know that g of y is just y cubed. And we set this equal to any constant. You don't need that part there. And so here is our capital F function set equal to an arbitrary constant. You can also see why if you had bothered putting a constant here, then there'd be a plus constant there, which you could just combine with the other constant. So you don't need to put any constant at that point. But this is going to be our general solution. Oops. My thumb hits the wrong button. And notice it's not explicit, it's an implicit, because y is not isolated. In fact, it's not always possible to isolate y. You know, it might very well be that the curve here is not a function of x or a function of y. In fact, if we go to Desmos, let's go ahead and graph this in Desmos just for curiosity's sake. Let's make sure we have it right first. Y e to the 2x plus y cubed. So y times e raised to the, there you go, 2x plus y raised to the third equals some capital C. Add a slide for C. Let's make sure I wrote that down right. Y e to the 2x plus y to the third equals C. And as C varies to different values, you get different solutions. So it does appear that this is going to be a function of x, but just because our solutions are functions of x, that would suggest that we could solve for y, get y isolated, but we have a y cubed with a y term. We are not going to go there and try to isolate the y. We're going to leave our answer written implicitly, but still general because of this, because of the C. Okay, so that is the process. We're going to do this a couple more times. Solve the exact ODE with given condition by hand. Use technology to graph the solution on the direction field provided. Okay, so here we go. We need to verify whether or not this is first an exact differential equation. Now, we're told it is, but we're going to verify anyway. So I'm going to put this in the form m plus ny prime equals 0. So I'm going to move everything from the left side, sorry, from the right side. I'm going to move all that over to the left side of the equation, group the y primes together and factor out the y prime. So I'm seeing we have a 2y e to the 2x plus a 2x, and these are the only terms that don't have y prime attached, plus, parentheses, we have a 1 plus e to the 2x already attached to a y prime, but joining that will be a negative sign y. Factor out the y prime equal to 0. Okay, so let's identify the m and the n. There's the m part, and here's the n part. To verify that this is exact, we need to do m with respect to y and see what we get. Differentiate m with respect to y, partial derivative. We're going to get 2e to the 2x, and then plus the derivative of 2x will be 0, so that'll just go away with respect to y. And now let's do a derivative of n with respect to x. The derivative of 1 will be 0. The derivative of e to the 2x will be 2e to the 2x. And the derivative of negative sign y will be 0, because we're differentiating with respect to x. So these are the same. This means that the ODE is exact. So it's just confirming the information that we were given, that is exact. Now we go through the process. We construct f by doing an antiderivative of m with respect to x. I know it's really easy to get these confused when you're thinking in terms of x, when you're thinking in terms of y, but the more you practice this, the better you'll get, the fewer mistakes. So we do an antiderivative of m. Let me just rewrite what m is in there. 2y e to the 2x plus 2x with respect to x, and as a consequence of that antidifferentiation, we'll have an arbitrary g of y. Okay, so capital F is equal to, antidifferentiate this part here with respect to x. The 2y will stay, we'll get a 1/2. E to the 2x is the antiderivative. Canceling with the 2y and the 1/2 will cancel, leaving just a y, e to the 2x. Antiderivative of 2x is just x squared. And then we have our g of y. Okay, so we antidifferentiated m with respect to x. Now I want to differentiate this with respect to y, and then set that equal to n. So differentiate with respect to y. The derivative of y e to the 2x will just be e to the 2x. The derivative of x squared will go away to 0, because we're differentiating now with respect to y. And the derivative of g of y will be g prime of y. Now we want to set this equal to the n function. So we have e to the 2x plus g prime of y is equal to, and then go up here and copy n. It's 1 plus e to the 2x minus sine y. Okay. Now we solve for g prime. Notice that e to the 2x's will cancel. So g prime will be equal simply to 1 minus sine y. Now we want to do an antiderivative of this to go back to g. Antiderivative of 1 is y, and the antiderivative of negative sine y is positive cosine y. This was an antiderivative with respect to y. Now we can construct our function f. Therefore, f is equal to, make sure I have enough space here. I'm just going to copy this. We now know our g of y is just that part. And here's my complete f function. Now to get the general solution, let's get rid of that equals f and just put this equal to a constant. And we've just created a general solution. And it's implicit general. Implicit general solution. But we do have some initial data, so we can find a particular solution. But we'll leave it implicit though. I'm not going to solve for y. So we plug in, let's see, this is the y coordinate, 0 is the x coordinate. So we'll plug in 0s for x and 1s for y. So we got 1 e to the 0, 0 for x, that's gone, 1 for y, and 1 for y, cosine of 1. That'd be 1 radian, by the way, not 1 degree. This is equal to c. And we get a 1 plus a 1, so we get 2 plus cosine 1 is c. So our explicit solution will be y e to the 2x plus x squared plus y plus cosine of y is equal to c, and c is 2 plus cosine of 1. And this is our explicit, or sorry, not explicit, still implicit, because y has not been isolated. It's implicit, but it's now a particular solution, not a general solution. So here's our, I went ahead and I used the dfield.jar software to make a direction field. In order to do that, I had to solve this differential equation for y prime equals, because that's how you have to type it into the software. And then I did a window from -3 to 3 and -3 to 3 and did a direction field. Now we're going to go to Desmos though and graph our actual particular solution and see how it follows these arrows and goes through the point 0, 1. In fact, let's find 0, 1 right now. And it could be helpful to put our axes in here a little bit better. So let me put the x-axis in there, nice and clear. Right there. This is our x-axis. Let's get the y-axis in here, nice and obvious. That's good enough. And 0, 1 is a point right there. So I could just start right there and just sort of follow the arrows. And just following the direction field, it looks like our solution's going to descend through there and then follow the arrows and maybe do an asymptote. And following the arrows backwards the other way, it looks, I don't know, something like this if I followed those arrows backwards right. Maybe it's a little hard to tell what exactly the arrows are doing, but I'm just trying to follow the direction field, this way as the graph is drawn, in such a way that we go through 0, 1. Okay, let me get rid of those, and let's test it. Let's do our I'm going to type in the general one, and then we're going to fix c to be 2 plus cosine 1 and see what happens. Okay, y e to the 2x. Let's go and delete that and delete that. We have, there we go, y times e raised to the 2x. Next term was, I'm going to make sure I get this in here right, x squared, then y, then cosine y, plus x squared plus y plus cosine of y is equal to, and then I'll put an arbitrary constant there and add a slider. Okay, make sure I enter that in right. Yeah, looks good. And then as you do various choices of c, look at the different kinds of weird solutions we get. And in particular, we wanted c to be 2 plus the cosine of 1. And there it is. There is our solution. Let me zoom out, and you can see it's sort of this wavy, curvy thing. Oops, let me hit the home button, go back to regular zoom. Now zoom in. We're clearly going through the point 0, 1 as expected, and our arrows, given our field of vision, which was -3 to 3, so roughly this field of vision right here, this is our solution. And notice it does cross the x-axis. I did not anticipate that. And then maybe it crosses it a bunch of times and sort of oscillates around it as it follows it like an asymptote. But coming back over here, I'd make a few little corrections here. Probably get rid of that, and it does turn out, in fact, it does cross before it follows these arrows again. Something more like this. Okay, this is good enough. Last one. Solve the ODE using 1, separation of variables, 2, an integrating factor, and 3, the method for exact ODEs. Notice that this one here is one of the ones from an earlier slide. It's just this one right here. This is the one that was all 3. It was linear, it was separable, and it was exact. So we are able to do a variety of methods. Let's start with the separation of variables. So I'm going to solve for the y prime. We have y prime, which is the same as dy dx, is equal to negative, then we had cosine divided by sine. That was going to be a cotangent, where I'm just dividing essentially both sides by -4 sine x to get y prime isolated. So divide -4 sine x. So the negative came from the 4 over -4, and we have a cosine over sine, that's a cotangent. We could leave it cosine over sine if that's helpful. In fact, it could be helpful if you want to do a substitution. And then times a y. Okay, so there's our y prime isolated. This is separable, so we're going to move the 1 over y to the other side with the dy and multiply the dx to this side. Negative cosine x over sine x dx. Now I'm going to integrate both sides. So integrate. The left side we integrate with respect to y. It gives me a natural log of absolute y. And the right side, you're going to have to do a substitution on this to finish. If you have the antiderivative cotangent remembered, great, but if not, then leaving it as cosine over sine is useful, because if you do a u is equal to the sine of x, then the du will be a cosine of x dx, which I have, right there. So there's my du. So this is really just a -1 over u du, and the antiderivative of that is natural log of u, negative. And u is cosine of x. Sorry, sine of x, not cosine. And then plus e. Now exponentiate, well, we got a few things to worry about here, to think about. This negative, we don't want that to stay in front of the natural log. I'm going to bring it up as a exponent on the argument. And this makes not arc sine, not sine to the negative 1, not an arc sine, but the sine of x raised to the minus 1 is 1 over sine, so that's cosecant. So I could write this as, let me put that down here again, as natural log absolute y is equal to natural log of cosecant of x plus c. And that was just convenient so that now when I do the exponentiate each side, I don't have that negative in the way. So we get absolute y is equal to, and we're going to break this apart to e to the natural log of cosecant of x times e to the c. And when I solve for y, I get plus or minus e to the c times the, and then here e to the natural log cancel each other as well, so we get absolute cosecant x. And then this I can just call another constant a. That was a plus minus e to the c. And then we have that in absolute value. Let's leave those absolute values there for the time being and see if we can make some conditions where that wouldn't be necessary. Right, to do an integrating factor, you're going to have to look back maybe at your notes for that part there, but we wanted to get the y prime isolated on one side and then get the y term on the same side of it. So it's actually, I'm going to start right here and just add that cotangent of x times y back to the left side. So our form looks like y prime is equal to, or sorry, plus cotangent of x times y is equal to, and we get a 0 on that side. So now I'm going to do an integrating factor. If you recall from doing this, we're calling this one here, that's the f prime of x. So we want to say, well, what's f of x? What's the antiderivative of cotangent? Okay, so we want to do an antiderivative of cotangent, which is cosine over sine. And if we do the same substitution we did over here in green, let u be sine of x, then du will be that cosine of x. So this is going to be a natural log of sine when we're done. So f of x equals natural log of sine of x. Now we don't need the plus c at this point when we're doing the integrating factor. And the actual integrating factor is e raised to this f of x. Simplifies down to the absolute value of sine of x. Now the absolute value of sine of x is either positive sine of x or negative sine of x, depending on whether sine of x is positive or negative. Right? Just recall that if you say the absolute value of a, this is either, it's one of two things. It's either a or negative a, depending on whether a was positive or negative. And we just need, for our integrating factor, just a function. It can be positive or negative. We just got to pick one of the two. So we can effectively just get rid of the absolute values and just verify that this works if I just go with sine of x instead of absolute values of sine of x. And now we multiply both sides of the differential equation by the integrating factor. So I'm going to copy our differential equation. And we multiply both sides of it by this sine of x function. Distribute the sine of x. So we have sine of x times y prime plus, now cotangent is cosine over sine. So this becomes just cosine of x times y is equal to 0 still. And we recognize this, in fact, as the derivative of the result of the derivative of a product. And that product will always be y times the integrating factor, which in this case is sine of x. Let's just test it real fast using product rule. Derivative of the first, check, times the second, check, plus the first, check, times the derivative of the second, derivative of sine is cosine. So this works out. And the other side is just 0. And now we can anti-differentiate both sides. So we get y times sine of x. And the antiderivative of 0 is a constant. So we'll just put, the constant there. I like A for some reason in this context. Doesn't really matter what letter you use. And now divide by sine. So we get A times the cosecant of x is our general antiderivative. With the commentary on the absolute value, I could have safely removed them here as well, because this cosecant, absolute value of cosecant, is either plus or minus cosecant depending on where we are with x, and that plus or minus could just absorb into the a to get the correct coefficient. So we can just drop the absolute values over in this case as well. And what we're seeing so far is two different ways of getting the same general solution. Now I do leave it to you to verify that this general solution is in fact a solution to the differential equation, even without the absolute values, and so I'll let you do that on your own time. For this lecture though, let's continue forward and use one last method. Let me make sure I have enough space. I'll move that slightly. And that is we can start right here with this form, or better yet, start with that form. Start with that form, add the 4y prime over to the left side, so we have 4y cosine x plus 4 sine x times y prime is equal to 0. So this is our m plus n. Oops, didn't want to do that. This is this right here is our m. M is right here, plus n, which is that function, times y prime is equal to 0. Now notice this form we've already verified is exact. If you write your differential equation in this way, then it's not exact. So it doesn't look like it's exact. To be exact means that it can be written in a form that meets the conditions to be exact. So sometimes you'll have an equation, written this way, and the way it currently is expressed is not an exact equation. As soon as you express it this way, then all of a sudden it is an exact equation, and then we can solve it using our methods for exact. So I'm going to identify the capital M function and the capital N. Let's just verify again that it's exact. So if I do m sub y, derivative of m with respect to y, I get 4 cosine x. And if I differentiate n with respect to x, I get 4 cosine of x as well. So this tells us that, yeah, we do have an exact equation. Now let's go ahead and get our answer. Capital F will be the antiderivative of m, so 4y cosine x with respect to x, and then add an arbitrary g of y there. So capital F is antiderivative of 4y cosine x with respect to x is going to be 4y sine x, and then plus some g of y. Now I do the derivative of capital F with respect to y, so do f sub y, and we get derivative of 4y sine x. Remember, as far as y is concerned, 4 and sine x are constant. So it's just a constant times y, so the derivative will just be just that constant, plus our g prime of y. And then we take this and set it equal to the n function, and the n function is just 4 sine x. Solve for g prime. We get g prime is equal to a constant, or is equal to 0, which means g is just any old constant. We'll call it a. And then we take our function here and set it equal. Well, actually, when you find g of y, you don't need it to be a general antiderivative. You need it to be any antiderivative. So you can put 3 there as an appropriate function for little g, or you can put 0. 0 also works. Or you could have left it a general constant. You're going to see why it doesn't matter. Because the next thing I do is I take the f function, now that I know that g is just a constant. So I take our f function right here, put it here, and set this equal to another constant. And g of y itself was a constant. So really it's 2 different constants, but you can just combine the constants into 1. So it's as if you said g was 0 in the first place, and you just had all this equal to a constant. Right, so when you're doing this step here, you just need any function whose derivative is 0, and 0 is an example of that. And then, of course, solving for y, we're going to divide this c by 4 sine x, and the c divided by 4 just becomes another general constant, and then the 1 over sine of x becomes our cosecant. So in the end, we can say y is equal to some constant times cosecant of x. And once again, we get the same general solution. And this wraps up the lecture on topic 6.